I'm sure our fellow postdocs don't quite get it either. But quantum information and quantum science is based on the fact that when things get really small, things get really weird. And you can get some really awesome effects from that. And we use quantum science to take those awesome effects and make them do even cooler things. Like we can make really cool codes that are both unbreakable or, and at the same time, break any code. We can compute problems that are challenging to do and take a really long time on regular computers, hypothetically in seconds. So that speed up is really incredible. Quantum stuff's just weird because you don't know where something is at any one time, and you don't even know how it moves. So like you might get something that literally goes through a wall if you were in the large scale, and that's just awesome. And you can do some really cool things with that.
That is super cool. So how, Fiona or Dahlia, how small are we talking for quantum? Piper mentioned that it's, when things get really, really small, are we talking like the size of like an ant, or are we talking more like atoms and molecules?
So we're definitely talking about atoms and molecules. So what's often called the nanoscale. So a lot of quantum science and nanoscience go together. And so, for example, in my lab, over the course of my PhD in the past few years, I've been studying the world's thinnest magnets. And so it turns out that you can take a material called chromium triiodide that's only 3 atoms thick, and you can actually measure its magnetic signal, which is pretty awesome. There's also graphene, which is just a single layer of carbon atoms. And it's been shown that 2 layers of carbon atoms can actually be superconducting. So there's a really, really unexpected things when you make things really small, really thin, and just play around with atoms and molecules in this way.
That is super cool. And superconductors, I've heard of these. That's sort of like a regular conductor, like a thing that conducts electricity, but it does it really, really well, right?
Mm.
Awesome. Cool. So Fiona, anything to add to that before we move on?
Yes. I would like to kind of merge just the basic definition of what is quantum mechanics, based on what Piper mentioned, that it's basically the science that governs things that are really, really small, because as she said, things get really weird, just to reinforce that. So yeah, I guess basically in the center that we're all a part of, that's basically the thrust, this whole quantum thrust to make things that are interesting based on this cool and interesting science. Because I believe that most of the science that governs the more like macroscopic world or the larger world with bigger things, we've figured out most of that. And if any of you are doing science right now or physics within your classrooms, that's probably the science that you're learning. But if you give it a little bit of time, you'll get more into the weird stuff. And if it gets weird, it gets interesting. So yeah, we're doing the interesting part in this new like avenue of science. So to give you an example of the research that I am doing, for example, I have this material called tungsten ditelluride. All of the solid state people are probably like, ooh, okay, we're sick of this material now, even though it was interesting last year. So basically this material has one particular, basically when you get to the 2D, you see more interesting things like it becoming a quantum material, like a topological insulator. Whereas in the bulk, it's another type. You know what I mean? It has different features. You see this transition from bulk to the nano layers, where you see like this change in the electrochemical nature of the material. So some of the properties change with this like thinning down or getting smaller. So you're probably wondering why should we care about these small things in this macroscopic world? Because as scientists, we figure out how to use this science, this very small scale science, to integrate it into larger technology and larger things that are more, I guess, beneficial to you, like your phone. That's from superconductors, right? Like the flat screen. So even though it's the small scale science, we use the weird to create things that are interesting. The very weird.
Yeah, that is so cool that you're able to use all these weird properties at the quantum scale to kind of like create new technology now. And it's interesting what you were saying about how you could take something that would be a big chunk of something on our scale, but when you make it really, really small, so it's just 1 or 2 atoms thick, it all of a sudden has these really cool properties. And I think, correct me if I'm wrong, but I think a pencil is kind of a good idea. Going back to what Dahlia was saying, right? If you have the inside of your pencil is graphite, which is a whole bunch of layers of carbon. And if you shave those off just to one layer, that's graphene that you were talking about, right, Dahlia? So that's, yeah, that it's so interesting that that happens, and so cool that you guys are all studying the nature of these little teeny tiny materials. Super cool. All right, thank you, Fiona. Thank you, everyone, for that. That's really cool. Piper has a pencil
like this, and put a piece of tape on it, and push it really hard. There, you've made graphene.
Well, literally this morning, I took Scotch tape to some graphite to make graphene.
That's so cool.
So that is what we do. Because if you take tape, then you can make the material thinner. And then when you do it a second time, it becomes half as thin, and over again. And then eventually you can get down to 1 atom thick.
Wow. And that's something that you all can do at home. Get some Scotch tape, get a pencil, see if you can make graphene.
If you looked under a microscope, you would see some.
That is so cool. All right, so that is exciting stuff. But I would love to hear about, this field is so interesting and new. What inspired you to get into this field?
Basically, how interesting the research was. As I said, like the bulk, we've exhausted bulk and like large,
meaning like big things.
Yeah, bulk things and the science that like applies to that. Like been there, done that. Like classical 1 and 2, great. I was more so interested in learning more about this because even this whole thing of the quantum revolution, I feel like the next leg of science, and I guess it's general opinion now in physics, the next leg of science is going towards quantum mechanics, is using quantum mechanics. And I always thought that quantum was weird, just extremely weird, because I'm like, this makes no sense. How can something go through a wall? How can something be here and everywhere? Like, what? Okay, I was like, this is weird. I need to understand it more. And then the opportunity to do research that really applies this knowledge and forces me to understand it as best as I can. Because does anyone truly understand quantum mechanics? No. So I found it to be the most interesting. And the research basically brings to light all of these theories that we have on paper in a textbook. And I think that's fascinating, personally.
That is fascinating. Yeah, Piper, how about you? How did you get into studying quantum, even as an undergrad?
So it probably started in high school. I had no idea what science I wanted to study. I just knew I wanted to study science. I'm a second generation scientist, so it seemed on both sides. So it seemed like the only way to go, and I loved it. And then I decided I didn't want to do biology. It was too messy. And then I took physics before chemistry, and that's why I ended up being a physicist. Similar process of elimination in college. I took some of the more classical big stuff, kind of boring. I never didn't get really interested until I took quantum mechanics. And quantum mechanics was this fun class where we reached a certain point in the class and everyone just, their brains broke for 2 class sessions straight. My professor just had to keep repeating things because we just didn't get it. And that experience was really cool to me, and I wanted to get it. And I kept going from there. I'd also heard some really fascinating stuff about quantum computing in high school, and I thought that was a really cool field. And what if I could do that? And I've just kept seeking out quantum stuff because that's the math I like best. That's the physics I like best. So why not do it? And the research opportunities are pretty cool. And I've enjoyed what I've learned at Sequem, but I haven't been as directly involved with the quantum stuff, but I hope to be at some point.
That's great. Yeah, awesome. Well, good luck with the rest of that. That's so exciting. And Dahlia, how about you? How did you get into this?
Yeah, so I guess it's pretty similar that I just taking quantum mechanics classes, I just fell in love. But I think in my case, so in undergrad, I studied both chemistry and physics because I could never decide. And I think I took both quantum chemistry classes and quantum physics classes, and I just love them both. But I realize that they're ultimately just the same thing at the end of the day. And so even though the three of us are all studying physics as our primary degree, I think that quantum science really goes beyond just physicists. It also is a lot of chemists, material scientists, electrical engineers, computer scientists to try to work on the code as well. It really is just so many people working together from all different fields towards similar goals who all understand bits and pieces better. And so I think it's kind of fun because I do still have some of the chemistry and materials aspects in my day-to-day research as a physicist.
Very cool. That's awesome. And you, Dahlia, both you and Piper have mentioned quantum computers, and hopefully we will get some questions about that from our audience, because quantum computers are super interesting. And so if you're watching us right now, remember you can start entering your questions for our panelists at any time by using the Q&A function on your screen. We're looking forward to getting to some of those in just a little bit, but I have just one or two more questions really quick for all of you. So now that we've been talking about this, and my dog is obviously really excited about it too. I don't know if you can hear her barking in the background, but I'm sure that studying science, and especially quantum science, is not all roses all the time. And there might be people out there who feel like there might be some roadblocks that might keep them from pursuing this kind of science in school or as a career. So can you maybe tell us about one challenge that you've faced either in school or in your life that you've encountered as you've been on this journey into science and technology, and how you overcame it, or maybe how you're trying to overcome it now?
For me, I've always loved physics, basically because of the whole rationale thing, following a rational path. And I thought that I had like a cheat sheet in nature, classical physics, cheat sheet in it, because quantum, there is no cheat sheet. There's just math. But I had a passion for it, but going into physics, I'm a first generation college student. I'm also a first generation PhD student. So I realized that I didn't have like a parent or an uncle or a brother or sister to ask these like hard questions, when I'm working through my problem set, or to like be like, oh, I did it, so you can do it also. So I didn't have that kind of support. I felt like it was just me just chugging along. So, but I did, even if you're a first generation student and you're going into physics, you can do it because you can find your own community. You know what I mean? Your friends are like your chosen family. And at Mount Holyoke College, I had a group of friends. Like we were all women going to this college, and we were all like working on science. So I found like some of my closest friends who are like sisters to me now, and we're all physicists or ex-physicists, because some of them jumped ship as soon as undergrad was over. They're like, no. Computer science, engineering, goodbye. But I found like a support group with people. So you can still find people who can support you. You can find mentors. You can find that those 2 professors or 3 professors in your college who are actually good at teaching. I won't even get into that. Physics is hard for everyone, guys. But you can find a support group. Just look for people who can support you. And try to exhaust as many resources as possible, and reach out to other people who are like you in the field, even if you're just sending them like an email, because it's like you're not asking for money, you're not asking for a favor, you're just asking for information, and that's free. You know what I mean? So just reach out to people who you think might identify with you for support, because physics is hard for everyone. If you don't have the support at home or someone to lean on, you might not have, it might be a little harder, but it's not impossible. You know what I mean?
Yeah, that's great. Thank you so much for sharing that, Fiona. That's really great advice. Dahlia, how about you? Any challenges you've faced that you've had to overcome?
Yeah, so I guess I do think that it is really important to look for mentors and just seek them out. And the worst that will happen is they'll just ignore your email. But the best thing that can happen is that someone who you can reach out to for years to come, which I've been very fortunate with the professor from undergrad who I still keep in touch with today. So I guess in lab, there have been a lot of challenges as an experimentalist. But I think some of the most fun things are overcoming these challenges in creative and sometimes silly ways. So some of the materials that I work with are really sensitive to air, and will be damaged if you take them out into the air. And so we had to think, well, our collaborators are on different continents all around the world. How are we going to get these samples to them? And we figured out that we could use a bag sealer for food. So like those plastic bags that are sealed shut for food, that when you buy it, we figured out that we could buy one of those machines and seal our samples that way. And then they're safely able to be shipped all around the world. So I think that was kind of one of the more fun challenges that we overcame.
That is awesome. Thanks for that, Dahlia. Piper, how about you?
I, I probably have more specific incidents than an overall challenging path, because I've had a lot of support going into science, since my family was very science intensive. So when I was starting science, I was really good at it. I was really good at math, and science was first math. And then I hit AP physics, and science stopped being entirely just math. Or at least it was math. I had never heard of math being like that. Science indicating direction, what in the world? And I got through the first unit just fine. And then I hit the second unit, which is free body diagrams. And I completely failed that test. And this was incredibly traumatizing because I'm not a person who fails tests. And that was a really big learning experience for me. I actually had to ask for help and learn how to learn physics. And that was part of why I decided to do physics, is because the first thing that made me stop and take notice and go, yes, I have to work hard to be good at this. And I think there's this impression that physics is something that if you're a genius, it's easy and you shouldn't go in if you're a genius, if you're not a genius. And the thing is, everybody has a point where they completely do not understand it. And it's what you do at that point that matters. And learning how to learn, learning how to ask for help, that's really important. And recognizing that it's hard and that's why you do it is important as well. There's also times when it can be sort of frustrating. You hit a point where you feel like you're not doing what you need to do to get where you want to go. I've been having some trouble with my research project at CIChem. It's just feels a little bit like a dead end right now, and realizing that, yes, that's how you learn. But don't let anyone tell you it's supposed to be easy or that it's fun if it's easy.
That's great. Thank you for that, Piper. That's really good advice because, failure is a big part of everything. It's how we learn, and scientists go through it all the time, whether it's in school or it's when they're out doing experiments. So that's a really important part of what it means to be a scientist, is being able to take those failures and then learn from them and charge on. So thank you for that. So I had one last question, but someone from our audience has actually asked the same question, basically, is what are your goals when you get out of school? What kind of careers are you interested in getting in as a quantum scientist? And, maybe even if you could give us a couple examples of careers that people get into when they study something like quantum mechanics.
I mean, there's always industry and there is academia. These are the two rivaling forces in a graduate student's life, if they're in the middle. So you have jobs at the companies that you mentioned, like the Google or the IBM, because everyone's basically racing towards this goal of quantum science, using quantum science for technology. So if you're looking at industry, there are a lot of avenues for a quantum science researcher to kind of go into, especially if you have some coding background or some coding experience. And then there's the other path of actually teaching, becoming a professor, going that route. So yeah, and I think I was talking to someone recently, the lines between academia and industry for quantum science, especially this rush towards the quantum computer, is becoming a little blurry because even professors are consultants for companies. So it's more like the two divided forces are somewhat becoming merged at some levels to attain this goal that everybody wants. So you have more flexibility to kind of maneuver between the two if that's what you want to do, or you can go to the red or the blue side. You know what I mean? You have options if you have a lot of coding or some amount of coding.
Yeah.
I mean, yeah, that's what I think anyway.
No, that's cool. So it sounds like there's, you can take the path of staying in a university and being a professor and maybe teaching and discovering even more things about quantum mechanics as you do your research, or you can take your knowledge and go to an industry or a company like Google or IBM who are trying to actually build the things that the scientists are discovering, right? That connection between science and technology. And so you all mentioned quantum computers, right? That's one of the things that people are working on in all of those, all of these companies trying to make these quantum computers that Piper mentioned would be way more powerful and be able to do lots of cool things that perhaps our computers that we have right now cannot do. Cool. So Dahlia or Piper, anything to add to that?
Yes, so, go ahead.
Oh, I can go. But I was just going to say, Phoebe, I was very excited to hear that things are merging a bit in between the industry and academia, because I've been doing a lot of thinking about what I want to do after grad school, because as I've mentioned, that's where you get the experience you need to do fun things. But the other option that I've been looking at that I haven't heard raised is public policy, where you talk to politicians and people in charge of funding, and you say this is really important because this reason. And there's a lot of money going into quantum science right now. So making sure it goes to the right types of things and advocating for its importance is another important role. The other thing I'd say is interesting is there's a blurring between theory and experimental work and where you can find positions for that. Because I'm looking at a theory track rather than experimental, and realizing that skills that you would think are sort of applicable only to snooty academia positions, as some people might characterize them, are actually really useful. Like knowing how to learn things really fast, which is what you learn in a physics degree, is really applicable. And some of the hard coding skills you also have to pick up.
Cool. Dahlia, anything else on that before we move on?
Yeah, so building off of what Piper said, there are a lot of positions within the government to have scientists, so people with PhDs who are not politicians, to be able to advise how the government should spend its science budget. And so a lot of that has shifted a lot of funding towards quantum science for both industry and academia. And then there are also government labs that have jobs as well. So you could be the leader of a research team there. They also have a lot of facilities, like some of the world's largest magnetic fields are in US government labs, where people can come and take their sample and blast it in a giant magnetic field and see crazy quantum effects happen. So they have those in Florida and New Mexico are the two big ones. So there are a lot of jobs in that sector as well.
Wow.
And also with energy. So looking for ways to have, so the Department of Energy has a lot of labs trying to see how to incorporate quantum materials into cleaner energy sources.
Wow, that's amazing. There's a lot of different ways that quantum science is sort of immersing itself into our technology. Really cool. So we have just a couple more questions from our audience Q&A that are related that I want to get to quickly while we have just about a minute left here. Which is, Piper, someone is wondering if you could tell us a little bit more, or Dahlia and Fiona as well, about how you overcome failures when you're in school, particularly like in trying to understand concepts that you initially don't understand. What are some ways that you can get help or try to figure those things out if you're sort of feeling like, oh, maybe physics is too hard for me? You know, how can you overcome that?
Well, since it was mostly directed towards me, I think I'll start. So first is identifying where the problem is. So are you having trouble with the math involved, or you have trouble with the concepts? If it's the math, maybe you need to go back and look at a concept. So I have some holes currently in my calculus background, so I've needed to do some review there in order to look at the next step. If it's the physics, then reading a lot of different ways that it's explained. You typically won't understand the first way that it's explained, so you need to find like 3 other ways and then combine those and see what comes from that. Doing practice problems is useful, especially if you have somebody to talk to about it. If you have an educator who's really invested, that's how I got over the hurdle, is he just talked me through it like 5 times. Finding somebody that, like a video that can talk you through it if you don't have a good instructor. Finding the correct textbooks. The first textbook you're handed probably isn't good either. So find a different textbook. Look at how the equations connect. If you have this equation, what can you do with it? Why is that equation the case? If you're checking your answer on a problem, look at what happens when things get really big or really small with your answer. Graph it if you can. Just you pick up this toolbox of things that are useful. And it's a bit of trial and error personally. Like I have a very specific way I want to write notes because that helps me and various resources, but everyone learns in a different way. So I can't tell you how to.
It sounds like a big part of it is being persistent and, you know, not giving up, which it sounds like you do, which is great advice. And, you know, finding out, you know, what works with you by just keeping at it and getting people to help you. That's great. So before we're out of time, but before we go, Fiona or Dahlia, do you have any parting words of wisdom like Piper had before we head out for anyone who's interested in kind of studying science or maybe quantum science?
My final words would be that don't feel like this field isn't for you, because don't feel like you're not smart enough. Most of the people who stay in this field up until the PhD level is because they're persistent and because they do like what Piper said. They find a million different ways to attack a problem to get to the end and understand it. I can personally say that in my time as a scientist, the concepts that I've truly understood are the ones that I had to teach myself or basically hunt someone down to teach me. Like it sticks after you've like fought with it for a couple of days. So don't believe the myth of the genius scientist who does everything by themselves and reads a book once and knows everything. Just don't fall for it. That's not how real science works. It's a fight. And if it's not, that's great for you.
Thanks, Fiona. Dahlia, anything from you before we go?
Yeah, I mean, I think the advice is the same. Just talk to people. It's okay to admit, I don't understand this at all. Help me. And, you know, maybe that other person doesn't understand it so well either, but explaining it to you will help solidify it for them too. So I think just don't be afraid to admit that you don't understand something. And that's the only way that you'll be able to one day understand it.
Awesome.
Also, if someone makes you feel bad for not understanding, that's a problem that they have. Find someone else. That's not you, that's them.
Good point. Thank you, Fiona. Thank you, everyone. Dahlia and Piper. Fiona, thank you so much for joining us. I'm going to give you a chance to wave goodbye, and then you can go ahead and turn off your cameras and your microphones. And thank you so much for joining us. All right, we have a lot more going on over at MOS at Home. In fact, tonight, let me just pull up the title here for you if I can. There we go. We have an event going on tonight at 5 p.m. And it is called The Ripple Effects of a Pandemic. And we'll have a panel of experts from different fields to explore the biggest ripples emerging from the pandemic, strains to our healthcare system, pressures on the life sciences, and the looming emergency in public housing. It's going to be a really informative and impactful conversation. And you can find the link to register on our website, www.mos.org/MOS at home. You can also follow us on social media to see what else we're up to. And if you enjoyed this program, Please consider supporting the Museum of Science by visiting us at engage.mos.org/welcome. Your support will help us provide access to science experiences online and ensure that this content can be accessed from home at no cost. I will thank you again so much for joining us. We had a great time, and thank you so much to our wonderful panelists. We will see you next time. Thanks. Bye-bye.